The on-site guide is a useful little book packed full of information, but sometimes working out what it's telling us can be difficult, and not just for new starters in the trade. Take this one for example, a frequent question. I've seen this formula in the on-site guide, what does it mean? And it looks complicated. How is that going to help me? Let's get straight down to business. Appendix F of the on-site guide is about current carrying capacities and voltage drop in copper conductors. We are using Amendment 2 books and all page numbers refer to the Brown on-site guide. The formula, as shown here, will let us work out the size or CSA of a conductor, taking into account the various installation and environmental conditions that the cable is exposed to. The four most frequent conditions are shown here in symbol form. If we break down the formula into parts, what have we got? IT is the tabulated current carrying capacity of the cable. What does this mean? We are going to work out a theoretical value of current and then consult the tables to find a conductor that will take that amount of current. We call it I tabulated. Almost every installation condition will affect the cable and make its conditions more arduous. Just about everything we do to a cable will cause it to heat up. Knowing IT will help us to select the size of cable to install to avoid overheating. This symbol means equal to or greater than. The number on the left of the symbol must be equal to or greater than the number on the right of it. Look at the symbol. The arrow-shaped lines have a bigger gap on the left, so the bigger number goes on the left. The smaller gap is on the right, the smaller number. And an equals sign, equal to or greater than. The two examples given here will show this in action. 5 is equal to 5, correct. Or we could have 5 is greater than 4, also correct. And more on this soon. IN is the rating of the fuse or circuit breaker, the OCPD, or overcurrent protective device. The N stands for nominal value, or, as I imagine it, N is the number printed on the device. The breaker on the left has an IN of 40 amps. This is the number printed on the device. We say that the nominal current is 40 amps. The fuse has 5 amps printed on it. It has a nominal value of 5 amps. IN is 5. Then we come to the installation conditions. The four most common are shown here, and there are more shown in the wiring regulations book. These are things that are going to cause problems and make the conductor temperature increase. They tell us by how much the cable must be derated to compensate for the conditions. The whole thing then. The tabulated current carrying capacity of the cable must be equal to or greater than the nominal rating of the OCPD divided by whichever condition codes apply to it. And we will work through some examples very soon. How do we start with this formula? This is the calculation, and it's actually a lot easier to use than it looks. Start with IN. Find the rated value of the fuse or breaker that is printed on the device. If it's a 20 amp fuse, then IN is 20 amps. So easy. We will divide IN by some other numbers that we will select next. What are the installation conditions that apply in this case? They will all have different derating factors to be applied. If a particular condition does not apply, then we can eliminate it from the formula, as we will see. The little table here is a reminder of the condition symbols and their meanings. Go to the tables and find the derating factors to apply. Shown here are the table numbers and page numbers in the on-site guide. When we divide IN by the condition derating factors, we will get a number, an answer to the calculation. This will be IT, and we will then look in the tables for a cable current capacity that is equal to or greater than our answer. The tables will tell us the minimum size or CSA of cable that we need for that particular circuit. They will tell us what size cable should not overheat given the applied conditions. And that's all that we do. If we know IN and we know the C factors to apply, we can calculate IT, the tabulated current carrying capacity. Then we can refer to the cable tables and find the nearest cable current that is equal to or above the answer to the calculation. The table will then show us the cable size to be selected. There are different tables for different cables. The table for 70 degrees Celsius flat profile PVC cable is what we often call twin and earth. Now we can put the numbers to work and do a couple of worked examples. The question asks, a flat profile PVC cable or twin and earth is to be installed and will be protected by a 32 amp circuit breaker. It will pass through a wall where it will be completely surrounded by thermal insulation to a length of 50 millimeters and will need to be derated. No other conditions apply. Find the tabulated cable current carrying capacity required, IT, and choose an appropriate size or CSA of cable. From the question, we know that the nominal value IN of the breaker is 32 amps. The question tells us the cable will pass through a wall where it will be completely surrounded by thermal insulation to a length of 50 millimeters and will need to be derated. CI for insulation is table F2, found on page 169 of the on-site guide. Looking at the table, a 50 millimeter length of insulation has a derating factor of 0.88. Now we can solve the question. As no other conditions apply, we only need to consider CI. So IT must be equal to or greater than IN divided by CI. Putting the numbers into the formula, we have 32 divided by 0.88. Our answer is 36.36 amps. IT, the tabulated current carrying capacity, must be at least 36.36 amps. This means that to carry 32 amps through the insulation without overheating, we need a cable that will carry at least 36.36 amps under normal conditions. If we now go to table F6 on page 177, we will find a cable selection table for twin and earth cable. We will start in the column heading reference method C, clipped direct. Follow the column down until we find a current equal to or greater than 36.36 amps. The table shows this as 37 amps. Now move to the left hand side and the cable size to be selected is shown as 4mm twin and earth. And that's it. That is the cable size to satisfy this formula. So, in this case, we've chosen 4 square millimeter cable to carry a maximum current of 32 amps. It's important to note that the load will not increase above 32 amps. The load will stay the same, whatever it is. But the cable chosen is capable of carrying 37 amps in normal conditions and using reference method C, clipped direct. The calculation we've just done tells us that this 4 square millimeter 37 amp cable will not overheat as the 32 amps of current passes through the 50 millimeters of thermal insulation. Think of the thermal insulation as being the pinch point for overheating. What we have done is over-engineered the cable size to cope with the conditions caused by the thermal insulation. Another example then. This time we are told that a circuit is protected by a 15 amp BS3036 semi-enclosed or rewirable fuse. We must find IT and choose an appropriate size of twin and earth cable. As before, IN, the nominal fuse rating, is given in the question, and the installation condition factor to use is CF for fuses. The information and derating factor for CF is found on page 167 of the on-site guide. At the bottom of the page, the last 2 sentences tell us that CF, the derating factor for BS3036 fuses, is fixed at 0.725. BS3036 are semi-enclosed, rewirable fuses, and their use goes back more than 60 years, but they are still out there and still being used. We use this factor to allow for BS3036 fuses being slower to react to overloads. We don't want the cable overheating as we wait for the fuse to blow. So, we need a bigger cable size to absorb the heat. Let's answer the question. We have IN, which is 15 amps, and we have a derating factor for CF of 0.725. Divide one by the other, and we have an IT figure of 20.7 amps. The cable that we select must be capable of carrying at least 20.7 amps in normal conditions. Referring to table F6 on page 177 for twin and earth cable, we can look down the reference method C column where we find that 27 amps is the current carrying capacity, and moving to the left, this shows that we should choose 2.5mm cable. Those were single condition examples. What happens if we apply two or more insulation conditions to the same cable at the same time? This question tells us that a circuit uses a 20 amp BS3036 fuse and the twin and earth cable passes through 50mm of thermal insulation. The question asks us to find IT and to then find an appropriate cable size for the circuit. The question already tells us the nominal fuse rating to use, 20 amps. And we must select two derating factors to apply. These are CI for thermal insulation and CF for BS3036 fuses. Using the appropriate tables, we have IN is 20 amps, given in the question. CI is 0.88 from table F2 of the on-site guide on page 169. And CF for the fuse is 0.725 from page 167. We now have enough information to calculate the required current carrying capacity of the cable. IT will be 20 divided by 0.88 and by 0.725. It's good practice to calculate the bottom row first as an intermediate step. So we have 0.88 multiplied by 0.725, which is 0.638. This now leaves us with 20 divided by 0.638, a much simpler calculation. Working this through, we have IT for the cable, which must be at least 31.35 amps. Going back to table F6 again, we find that for an IT of 31.35 amps, 4 square millimeter cable must be chosen. So, applying two or more installation conditions is no more difficult than applying one condition. Just make sure that your calculations are correct. What do we mean by that? How do we know if our maths is wrong? A good clue that you have a wrong answer is if the answer for IT is smaller than the breaker size, or IN. Let's look at this. The only time that IT can be smaller than IN is when the rating factor, CA, for ambient temperature is greater than 1 and no other rating factors apply. At an ambient air temperature below 30 degrees centigrade, the rating factor CA is greater than 1, the only time it happens. So, how can we get the maths wrong? The most common error is entering the data into a calculator incorrectly. Look at the last question and let's answer it two different ways. Follow what happens here. If we put the values into the calculator as a simple string of numbers, we will have 20 divided by 0.88 multiplied by 0.725, which gives us an answer of 16.48 amps. Quite clearly, this is less than 20 amps. What we have done here is divided 20 by 0.88 to give us a certain number, and then we multiply that number by 0.725 instead of dividing it again. This is the wrong way to do it. We should imagine brackets around the two bottom numbers. we work out the brackets first. 0.88 multiplied by 0.725 is 0.638. Now we can complete the calculation. So now we have 20 divided by 0.638 and no chance of getting ourselves confused. Our answer then, IT, is 31.35 amps, and this is correct. A quick recap on what we've done. We take IN, the nominal value of the circuit breaker, and divide this by the derating factors in Appendix F of the on-site guide. The answer will be the tabulated value of conductor current. We are not going to increase the current that flows through the cable. What we are doing, in fact, is oversizing or over-engineering the cables to allow for any heating effects in the cables caused by the different installation conditions. Almost everything that we do to a cable will make its conditions worse. These two tables will guide you to the correct pages for the installation conditions to find the derating factors, and also the cable tables where we can compare IT to the current carrying capacity of different sizes and types of cable and make our choice of cable size. And finally, a reminder of the process from start to finish. And we do hope that this video has proved beneficial and that a little more knowledge is stored in your mental toolbox. A later video will look at the voltage drop part of Appendix F in the on-site guide to Amendment 2. Thank you for watching, it really is appreciated, and we hope that you found this video useful and informative. Please subscribe to our channel to get access to all of our videos, and remember to click on notify to be sure of not missing our next video. And you will find even more information, videos and help on our website at learnelectrics.com. And don't forget, you can also type in Learn Electrics, all one word, into the YouTube search bar to go directly to our channel at any time from any computer. We are constantly adding new videos to our channel, so don't miss the next one. And once again, thank you for watching, and we hope to see you again very soon.